If you live anywhere in Washington, Oregon, or California, you've probably seen the headline, "Atmospheric River," and suddenly it's flooding on one side of the state, feet of snow in the mountains, and you're wondering if your commute is about to be chaos. So what is an atmospheric river? Is it like a hurricane? A river in the sky? And why does it feel like the West Coast gets these over and over, especially in the winter? Stick with me here, because in this video I'll show you how a specific metric called IVT can tell you how seriously to take an incoming atmospheric river. An atmospheric river, or AR for short, is a long, relatively narrow corridor in the atmosphere that carries a huge amount of water vapor, basically the bulk of the horizontal moisture transport outside the tropics. It's not a river of liquid water. It's a river of gaseous water vapor and high winds. And when that vapor gets forced upward by a storm system, a cold front, or mountains like the Olympics, the Cascades, and the Sierra, it condenses and dumps out as heavy rain or mountain snow. To determine how strong an atmospheric river is, meteorologists often track a number called integrated vapor transport, or IVT. Think of IVT like the flow rate of water in your garden hose. The more water vapor there is, plus the stronger the winds that are pushing it, integrated over a vertical depth of the atmosphere, equals a higher IVT or stronger atmospheric river. And the stronger and longer that hose aims at one region, the greater the impacts of the atmospheric river. The keyword here is transport. It's not just the presence of humid air, it's a fire hose of moisture being moved by fast winds. The atmospheric river scale, used by the Center for Western Weather and Water Extremes at UC San Diego, was described by Ralph et al. 2019 in the Bulletin of the American Meteorological Society. It categorizes ARs by considering its intensity, with a threshold of 250 kilograms per meter per second, and combining it with its duration in hours. The higher the number, the stronger the AR. So why is it that when it comes to atmospheric rivers, the West Coast can go from "we need water" to "we have way too much water" in such a hurry? And why is this so often a winter story? First off, atmospheric rivers are global. They occur all over the world outside the tropics and are most common in the mid-latitudes. But for the US, the West Coast stands out for a few reasons. Number one, the jet stream. In the mid-latitudes, we're often under the prevailing westerlies, meaning winds like the jet stream generally flow from west to east. That means storms and their moisture plumes come off the Pacific and move toward the West Coast. Number two, geography. The West Coast is filled with north-south mountain ranges such as the Olympics, Cascades, and the Sierra Nevada, all of which sit perpendicularly to the prevailing westerlies. So when an atmospheric river slams into those mountain ranges, the heavy rain and snow ramps up fast. Number three, a large ocean. The Pacific Ocean gives storms a huge stretch of open water to organize that corridor of moisture. Yes, there are absolutely atmospheric rivers in the Atlantic too, but the US West Coast sits right where the typical Pacific storm track runs into big terrain head-on, which makes the impacts more obvious and often more intense. So what's the deal with atmospheric rivers happening more often in the winter? Well, in the winter, the jet stream is stronger and the Pacific storm track is more active. So you get more frequent setups where a storm taps subtropical moisture and focuses it into a narrow corridor. By the way, even though cold air holds less water vapor, as I had explained in my other video about relative humidity versus dew point temperature, link is pinned in the comments if you haven't seen it already, winter is often also when the winds are fastest. And IVT is basically moisture multiplied by the wind. So the stronger prevailing winter winds can move a ton of water vapor, leading to a higher IVT even if the moisture isn't necessarily more than what you'd find in the summer. Historically, scientists used origin-based nicknames like Pineapple Express to describe a strong AR pattern where moisture builds up around Hawaii and streams toward the West Coast. The broader term atmospheric river came into use in the scientific literature in the early 1990s, and you'll now hear it more in forecasts because it covers all these moisture corridors, not just the ones that come from a source region around Hawaii. Alright, quick shout out here to my longtime friend Dr. Jay Cordera, an expert in atmospheric rivers who wrote this research paper published in 2013 in Monthly Weather Review. He and his co-authors investigated two atmospheric rivers that ended up producing over 200 millimeters of rain in mountainous Northern California in late October 2010. What's wild is where some of the moisture and energy came from. Their analysis showed that those ARs developed in environments connected to western North Pacific tropical cyclones, with water vapor transported toward an intensifying North Pacific jet stream. In other words, sometimes an atmospheric river isn't just Hawaii moisture, it can be this giant multi-stage conveyor belt where the jet stream helps focus moisture into a narrow corridor, and then that corridor stays alive as more moisture gets fed into it along the way. And they also show something that matters for forecasting impacts. Even while precipitation is wringing the water vapor out of the air along the AR, a lot of that loss can be offset by moisture converging into the corridor, basically the atmosphere refilling the fire hose while it's raining. That's why you can look at a satellite or radar image and think, wait, why is this band not moving or weakening? Atmospheric Atmospheric rivers can be stubbornly persistent, and that's because the large-scale atmosphere is literally designed to keep feeding it. So why care about atmospheric rivers? Well, even if you're nowhere near the coast, atmospheric rivers matter because they're a huge part of how the American West gets its water. On average, 30 to 50% of annual precipitation in West Coast states can come from just a few AR events, which is why they're both water supply heroes and flood risks. It's the same system that can fill reservoirs and build snowpack, or if it stalls over vulnerable terrain, can trigger flooding, landslides, and travel chaos. It's a classic case of how too much of a good thing happening all at once can become a bad thing. If you like weather science broken down into simple terms like this, I'm here to empower you to cut through the hype of social media and know how best to interpret extreme weather headlines. Hit subscribe and drop a comment about what you'd like to learn about next. Also, be sure to check out this video here, where I explain the difference between relative humidity and dew point temperature, and also this video here, where I break down the differences in winter precipitation. Stay tuned as we navigate through this crazy season of winter weather together.